All right, let's start. Once again, reminder for you, exams Thursday, 6:30, same place, same as the previous exam, same time. I am aware that some of you have an exam right after hours. That's in a different place. So it's very important that everybody gets there on time so we can start the exam on time so we can get you out of there on time. Okay? And looking at the calendar here, we'll cover one more lesson that's not going to be on the exam. And Wednesday, we'll do review lecture, like we've been doing with the previous two exams. Thursday, you have a review recitation, and there is a class on Friday. However, the next Monday and Tuesday, you do not have MA 161 lecture or recitation. All right, so we're going to be looking at two sections simultaneously today. This is sections 5.1 and 5.2. And remember, this is not on exam 3. Okay, so now we got to the part of the calculus where we're going to be looking at the area of stuff. So the kind of problem we'll be looking at, so-called area problem. The idea is to find the area under some graph f of x from x is equal to a to x is equal to b. Okay, some kind of graph, and underneath that there's some kind of area, and we want to look at the area from a to b. And let's look at a more concrete example as the motivation. For example, what is the area under f of x equal to sine of x on the interval, let's say 0 to pi over 2? Okay, that kind of thing. Given a function, how do we find the area underneath that? Of course, implying that the portion above the x-axis. There's the portion below x-axis. That's an extra layer of complexity. We'll get to it later, but for now, we'll focus on the simple case. So graphically, here's what we're looking at. Imagine the graph of sine. It continues on, but we want to chop it off at pi over 2. This is 0. At pi over 2, sine reaches 1. So this kind of a quarter, almost a quarter circle kind of area, region, is what we're interested in. Now, if this were an elementary shape, like a square or triangle or something, we could find that very easily. But this is not. There's a curved portion on the top. It's not exactly a circle. So finding the area is a little bit more complicated. Today, we're going to focus on the basic way to approximate this area, or rather simple way to estimate is to use what's called a Riemann sum. Okay, Riemann was a German mathematician, lived in the 19th century, did lots and lots of work, and he formulated the algorithm we're about to see and gave us a way to estimate. We're not going to be able to find the exact area just yet, but we can use the simple geometry to find out an estimate of the area. And it's an estimate that we can make as good as we want. Okay? So let me show you the idea, the basic idea. The idea is to divide a region into a bunch of rectangles. Then we sum the areas of those rectangles. Rectangles are simple. We know the area, length times the width. We chop this up into a bunch of little ones, and then we add them up. And in the end, we're going to get something that should be, and well, depending on what you're doing this for, but hopefully a reasonable estimate of the area. Okay, here's how it works. So let's use the same function, sine of x, from 0 to pi over 2. Make a big sketch in your notes. We're going to be adding quite a bit of things to it. So make sure you make it big enough so you can add things without it being too crowded. All right, we know what this looks like, right? This is the first quadrant portion of the sine graph. Starts at 0, curves up to 1 at pi over 2. The first step here is to look at the x length here from 0 to pi over 2. We'll divide this into n equal intervals. N is a number you choose. Divide the x length into n equal intervals. Here as an example, let's use n equal to 4. But that's a number that you choose. If you want 5, 5 is fine. 6, 10, 18, don't choose pi. You can't do pi intervals, right? That's not going to be a good number to do, but some nice integer you can work with. So I want to chop this into 4. So make one cut here that makes it go into 2, and that's going to be pi over 4, of course. Each one of these I'll further chop in 2. Okay, so between 0 to pi over 2, I chopped into 4 intervals. So my x goes from 0 to pi over 8, 2 pi over 8, 3 pi over 8, and then 4 pi over 8. 4 equal subintervals. So after doing that, this is what we ended up doing. And now we're going to represent each of these strips as using a rectangle to kind of estimate the area. For example, I'm going to use, the idea is to use rectangle. Rectangle is simple. Now, if you look at the case right here with the first one, I can estimate the area underneath that green curve by using a rectangle. Because I'm constrained to using a rectangle, my choice is not very, I don't have a whole lot of choices. This is the kind of rectangle I could use to represent the area of the first subinterval. Notice what happened here. Look at the first subinterval here. I used the right end of that subinterval to come up with the height of the rectangle. Here we use the right end of each subinterval to give us the height of each rectangle. Okay, then I duplicate that process for the remaining subintervals. Looking at the second one here, I move to the right end of that. And from there, I use that where it touches the curve to draw the height, to draw the top of the rectangle. Right here. So this second one, this is the rectangle that's going to represent the area under the curve. Now, as you can see, we got portions of the rectangle sticking out. Well, so because we're using a very simple shape, we're getting an estimate, not the exact answer. Third one, and then the fourth one. Now, if you just eyeball this thing, if I add up the four rectangle areas, I'm going to have something that's going to be a little bit over what I should be getting. But it should be pretty close to what the area should be. Right? Do you agree? It's not going to be exact, but it should be pretty close. So let's see. Now we add up rectangle areas. The notation we use in this book, because I chose to use the right endpoint of each subinterval, I'm going to write a capital R that represents, we use the right end of intervals. And then the subscript tells me how many rectangles I've chosen to use. I used 4. So R4, we used 4 rectangles. And this is going to be approximately equal to the true area. Okay, and now here we just add up the 4 rectangles. Look at rectangle 1. It has a width of pi over 8, right? And rectangle 1 has a height. At this point right here, the point that touches the y-axis is f of pi over 8, which is equal to sine of pi over 8. Right? Notice I chose the right endpoint, which is pi over 8. Where it touches the green curve, the sine curve, I move over. That tells me how high the first one is. So the first rectangle is going to have an area of pi over 8 times sine of pi over 8. This is the width of rectangle 1. This is the height of rectangle 1. Okay, does that part make sense? Just the first rectangle. If you get the first rectangle, everything else is just straightforward. Everybody clear how we got that? Yeah? Okay. Let's go to the second one. Second one has the same width. That's why we divide into equal intervals. So 1, 2, 3, 4. Still going to have a width of pi over 8. Now, how high is the second one going to be? What's the height of the second one? Right, and how'd you get that? Sine of pi over 4, right? Absolutely. So sine of pi over 4, you look at the right end of the second subinterval, look at where it hits the graph. That's on the graph where y is equal to sine of pi over 4. Continue. Rectangle 3. And finally, rectangle 4. All right, let's make this more clear. This is rectangle 2, rectangle 3, and 4. Any question about this stuff? Once you get this idea, variations of this is just straightforward, but you have to understand how we came up with these 4 things. All good? All right. So let's see what we end up getting. For this part, you're going to have to use a calculator for some of those numbers, but that's okay. So we end up getting an R4 that turns out to be, if I add all of this stuff up, I get something around 1.183, which is going to be approximately, remember, the true area under sine of x on the interval 0 to pi over 2. Now, is this number 1.183 overestimate or an underestimate? Over, right? It seems pretty clear because each rectangle has a little bit of each one that's sticking out above the curve that we don't really want, but we're included anyway. So we know this is an overestimate. Because each rectangle has part sticking out above the graph. All right, let's try a variation of this. This time, let's use the left endpoint of each subinterval to estimate the area. Okay, now let's try using left end of each subinterval for height. The obvious choices are left and right. There are also more complicated choices like midpoint. We're not going to worry about midpoint. We're just going to worry about left and right. Okay, same idea. Here's the portion of the sine graph from 0 to pi over 2. Same steps. The only thing that's going to be different is where we find the height. So let's just keep everything the same. Again, let's use n is equal to 4 rectangles. Okay, so we chop in 2. Each one chopping half again. All of this, these are all the same numbers before. 1 pi over 8, 2 pi over 8, 3 pi over 8, 4 pi over 8. Go straight up from each one of these where it hits the curve. That's going to help us determine the height of each one. And now we use the left end of each for finding height. Exactly the same thing we just did, except this time we're switching where we find the height. Okay, now look at the first rectangle here. How tall is it? Right, 0, right? If I go to the first end point here, the left end is 0. So my first rectangle actually is just a flat line. That's all right. Yeah, that's all right. Second rectangle is going to have a height formed from the left end point of the second subinterval. So here's the second guy. Now here's the third one, right? Third subinterval, left end point where it touches the curve, that's my height. Fourth subinterval, where the left end point touches the curve, move over, that's my subinterval. It seems pretty clear that this will be an underestimate. Do we agree? Yeah, we're missing here, 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 and here. The last one was an over, this one's an under. That's okay. There's just different ways to estimate the same thing. You want to be on the conservative side, or do you want to be a little bit more daring with a little bit over, depending on what the application is. Here we're using left end point, so we write an L. We're still using 4 subintervals, right? First rectangle has a width of pi over 8. It has a height of sine of 0. Left end point of the first subinterval is 0. Question there, guys? Good? Okay. Second rectangle. Left end point is pi over 8. So where it touches the curve, the y value is sine of pi over 8. Height of the second. Third. Now the fourth. Okay, is it clear where each of these numbers came from? Yeah, if you got the last one, if you got the idea from the right one, the left hand one is the same thing. Okay, so this turns out to be something around 0.791. And we know just by looking at the picture, this is going to be an underestimate. Okay? Now, I still don't know exactly what the area is, but after doing these two things, I can say with 100% certainty that the true area is somewhere between something no smaller than 0.791 and something no bigger than 1.183. That we know for sure. I can give you a window where that area is going to live in. You could average, but how good that average is depends on what the curve is doing. Okay? What's that? Right. We'll get to that in a little bit. So we can say that the true area is going to be something between 0.791 and 1.183. Right? I gave you at least a window now. I know this is going to be true. No bigger than about 1.2 and no smaller than about 0.8. So whatever the true area is, now we narrowed it down. Okay, now the very logical question is how do we improve that? Now, one easy way to do that is to use more rectangles. And I'll show you why. We can improve either one or both. That's right, either or both by using more rectangles. That means higher n. Okay, let me show you why that's true. Look at the curve that we have been looking at. Still looking at this sine curve here. Pi over 2, let's stick with 4 for now. Pi over 4, 3 pi over 8. Nope, 1 pi over 8. 3 pi over 8. Now suppose we'll use the left endpoint. We'll just look at the second rectangle here. Just look at one of them, you'll get the idea. That would be right. Sorry, right. Right. You're right. No? Okay, fine. The right endpoint of each one. Okay, now this thing right here is the area that we don't want. Now below that, let me sketch what happens if we had used double the number of rectangles. So I'm going to try to duplicate the graph right below it. Try to make everything as close to the same as possible. So the top graph is n is equal to 4. The bottom graph, n is equal to 8. So we're going to chop everything in 2 again. Okay, now notice that when you use 8 here in the second part, line them up here, the big area that we didn't want in the first case, now we remove the portion of that by using smaller rectangles, thinner rectangles, right? So if you line these things up, this red part we remove this by using n is equal to 8. That entire thing used to be the excess part we had from n is equal to 4, and now by using 8, we remove that little portion. So the portion that we include, that we shouldn't include, is now smaller. So the excess area is now smaller. And what that means is we're going to get better estimate. However, by doing that, there's a price. We're going to have to sum up 8 rectangles now to get an estimate. So we do essentially double the amount of work for a little bit of the payoff here. It depends on, I say a little bit, but it depends on what the curve is doing. Sometimes the payoff is pretty good, sometimes not so good. It all depends on how this thing is curving around. The idea is the same if we had used left endpoints. Okay, so the short story is the more you use, the better it is, regardless of which one you use. Now, if you can somehow manage to use infinitely many rectangles, then the area would actually be exact. If you could use infinity rectangles, the area you get would no longer be an estimate, but would be exact. But the more you use, the better it is. That's the takeaway from that. Okay, any question on this Riemann sum idea? You have plenty of chances on the homework to try it out, but does the idea make sense? Yeah? Okay, good. All right, now let's do a little bit of things that we're going to introduce a new symbol and a little bit of math here and there. It may look a little intimidating, but just take these things one line at a time. Okay? So in general, the area under f of x on the subinterval, on the interval a to b, using n rectangles, can be written as this. We'll call the area A, and that's going to be roughly equal to, same thing we've been doing here. We sum up the area of each one. Let me write down a few of these and you'll see how they work. Okay, we'll stop with that for a moment here. Let me explain these pieces. This delta x business, this is the width of each one. Look at the simple example we did with the sine curve there. Our b was pi over 2, our a was 0. So we divided into 4. We took the length b minus a divided by 4. That's how we ended up getting pi over 8 for each rectangle in the simple example we did. So that's the width of each one. And notice they're all the same. Now this f of x1, this is the height of rectangle 1, where x1 is either left or right end. So if I had chosen left, then for the first one, the left x1 would be 0, and so on. F of x2, so on. So this keeps going. The third one, and then the fourth one, and the fifth one, all the way up to the nth one. Okay, so if I choose n rectangles, I do this n times. Each one is the height times the width. Very simple. And I have n of those guys. Now, let's write this. Notice that because of all of these guys have delta x, we could actually factor them out and rewrite it this way. Plus dot, dot, dot. Right? I can factor out the delta x from each one of them and put it after that. If I'm summing up a bunch of things, there's a shorthand notation for that. You might have seen it before. It's the sigma notation, summation, that means sum. We'll start summing at I is equal to 1 all the way to n. And instead of writing x1, x2, x3, I just write x with a subscript I. So what this does is that I put in I first, that gives me that. Then I move 1 up, that gives me that. I is equal to 2, and then I is equal to 3. And I stop when I hit I is equal to n. Okay? Now, if you take 162 next semester, we'll be doing a lot of this sigma stuff. But for now, don't worry too much about it. And then all of these guys have a delta x at the end. The area is exact if n goes to infinity. The more n we use, the better the estimate. If in the limiting case we let n go to infinity, what we end up getting is the exact answer. So this thing is actually equal to the limit n goes to infinity of that thing which we often drop the limit and just sum it from 1. And don't stop at n, but we stop at infinity. Of course, we can't stop there or get there, but that's the notation. And once again, in 162, we'll be doing lots of stuff with that. For now, don't worry too much. We don't want to write this over and over again. So there is a shorthand notation. Okay, we write it this way. Instead of writing this sigma from 1 to infinity, we write out a stretched out letter s. It's the letter s stretched out. Now, instead of counting rectangles, now we just note where we start. We start at x is equal to a, so I put it near the bottom of that. We end at x is equal to b. This is where x starts, where x ends. So what's going on here is because we're using an infinitely many of them, we stop caring about each one. We care about the whole thing. The whole thing starts at A and ends at B. Now, right next to it, I write f of x. And then this delta x, when it shrinks, becomes dx. So these two are the same thing. This thing is called a definite integral. Okay, now, there's a lot of stuff on there. The thing you want to take away from the last page is that if you see that funny looking thing at the bottom, that just tells you an area under a curve. That's the minimum you need to take away from that page. I'll write that down. So this thing right here represents area under f of x on the subinterval a to b. Okay, that's the minimum takeaway from the last page. They can represent a bunch of other things. If f of x is the velocity, then the area under it from x is equal to a to x is equal to b is the total displacement from a to b. So the meaning of that depends on what f of x represents. In the pure, most basic way, all it shows you is the area. But suppose it is the velocity, then you end up getting the displacement. If f of x is force, then what's underneath is work. Then area under is work. Very often we can find areas without much work. Not the same work. That's a poor choice of word, but work in the sense of adding rectangles. Anyway, you get the idea. For example, if you could visualize what kind of area you're dealing with, a lot of times there's really nothing to do. For example, if I'm looking at the area underneath the curve f of x is equal to x from 0 to 3, so here's f of x equal to x, starting at 0, ending at 3. And of course, that's also equal to 3. Now, if you look at it, if you can translate this into that, then the answer is staring right at you. This is a triangle with a base of 3 and a height of 3. So the area is equal to what this thing is representing. We know the area of a triangle with a base 3 and the height 3, and that's 9 over 2. Right? If you can tie this into an elementary shape, then you don't need to do that Riemann sum stuff because you don't have to. You know the area. You only do Riemann sum if you have a complicated shape that you can't deal with in the most elementary way. Let me show you one more example. Okay, let's think about what this is representing. Anybody recognize what this is? What shape this thing is? Radical 16 minus x squared. circle. Yeah, it's a circle, right? It's the upper half of a circle, right? Upper half of a circle with radius 4. But the portion that we care about is from 0 to 4. So we care about this portion. Right? Again, it's an elementary shape. We know the area. So this thing here is representing the area in the green shaded region. It's a quarter circle of radius 4. So here's the circle radius 4, pi r squared over 4, right? This portion is circle with radius 4. 4 because we want 1/4 of it. So this turns out to be 4 pi, of course. Okay. There's some useful properties that you want to know. If you're looking for the area of f plus g, underneath f plus g altogether, it turns out that you can just find the area under each one of them separately. Sorry. And this works for plus and minus. Right? You just preserve the sign between the two. F plus g, the area underneath that, is the same as the area under f alone plus the area under g alone. If it's a subtraction, then it's an area under f alone minus the area under g alone. And I can show you a very simple example why that's true. Okay, so this thing right here represents this entire thing. But notice that we could also make it cut right here. And this thing really is just a rectangle plus that. So this is really equal to as if we had taken that triangle down here. This is a 3, and that's a 1. Oops, sorry, that's a 3. Sorry. Plus that. Okay, so that's the idea behind that. If you have two things stacked together, the total area underneath can be chopped up by just taking them apart. So this right here is representing 0 to 3 x dx. And then this guy here is representing 0 to 3 of 1 dx. Right? You get a triangle, you get a rectangle, stack them together any way you want, and you get a total combined area. Okay, that's it for today. See you Wednesday. We'll do review for exam 3. Okay?